Hello everyone, and welcome to our session on identifying dominant terms in BigONotation. Today, we're going to explore how dominant terms in mathematical expressions determine the growth rates used in Big O analysis. We'll discuss how recognizing these terms is crucial for simplifying complex expressions and for evaluating the efficiency of algorithms. Whether you're working in algebra, calculus, or computer science, understanding how to pinpoint the dominant term is essential for making accurate performance predictions. Let's dive in. Let's begin by defining dominant terms. A dominant term is the part of an expression that has the greatest effect on its value as the variables approach a specific limit, often infinity. For example, in a polynomial, the dominant term is the one with the highest degree. This term is key because it determines the overall growth rate of the function and plays a critical role in evaluating limits and in BigONotation. Identifying dominant terms in program. Let's jump into the Visual Studio Code. I'm going to implement a program that includes a function called example function to demonstrate different time complexities within a single function. How it works. We start by defining the function example function that accepts an integer input, n. The purpose of this function is to compute a result by performing operations with varying complexities. At the beginning, we have a simple assignment. Int result equals 0. This is a constant time operation big O, 1, because it takes the same amount of time regardless of the value of n. Next big O, n, linear operation. We use a for loop that runs from 0 to n1. In this loop, we add each value of I to result. Since the loop iterates n times, this operation is linear big O, n. Next we have big O quadratic n operation. We include a nested loop. Here, for every iteration of the outer loop, the inner loop runs n times, leading to roughly n times n or big O quadratic n squared operations. This quadratic component dominates the overall time complexity. Although the function contains big O, 1, and big O, n, linear operations, the dominant term is the big O quadratic n squared operation. Therefore, the overall time complexity of example function is big O quadratic n. In summary, by defining and using example function, we demonstrate a mix of time complexities. And big O, 1, operation for initialization. And big O, n, operation for a simple loop. And big O quadratic n squared operation through nested loops. Since the big O quadratic n squared part grows the fastest as n increases, it determines the overall performance, making the function a clear example of a dominant term. To summarize, the dominant term is the part of an expression that largely determines its behavior in extreme cases. Identifying it generally involves comparing the exponents of the terms and, where necessary, their coefficients. This understanding is essential not only in theoretical mathematics but also in practical applications like algorithm analysis and scientific modeling. Mastering this concept can greatly simplify the analysis of complex functions. Thank you for your attention, and I'd be happy to answer any questions you may have.